A paradox is not a trick question. It is what happens when two statements, each individually supported by overwhelming evidence, directly contradict each other. Not a riddle with a clever answer. A genuine contradiction sitting at the foundation of how the universe appears to work. Science has solved enormous numbers of these over the centuries. Each solved paradox became a discovery. Olber's paradox revealed the universe is expanding. The ultraviolet catastrophe gave us quantum mechanics. But some paradoxes have not been solved. They have been studied for decades, sometimes centuries, by the best physicists in the world, and they remain exactly where they started. Two true things that cannot both be true. Here is every major one. 1. The black hole information paradox. Quantum mechanics contains a principle so fundamental it is rarely stated explicitly. Information cannot be destroyed. The complete physical state of any system, no matter how it evolves, can always in principle be reconstructed by tracing the evolution backward. This is called unitarity, and it is one of the bedrock assumptions of quantum theory. General relativity says something that directly contradicts this. When a black hole forms and matter falls into it, that matter is gone, sealed behind an event horizon, causally disconnected from the rest of the universe. In 1974, Stephen Hawking showed that black holes are not eternal. They radiate Hawking radiation, and over an astronomically long time they evaporate completely. Hawking's original calculation showed that this radiation is purely thermal, completely random, carrying no information whatsoever about what fell into the black hole. If a black hole evaporates entirely, and the radiation it emits is genuinely random, then whatever information fell in has been permanently destroyed. Many different objects that fell in could have produced the exact same final state of radiation. Quantum mechanics says this cannot happen. General relativity, combined with Hawking's own calculation, says it does. Both frameworks are among the most rigorously tested in physics. Physicist John Preskill called this potential conflict a sign that the puzzle of black hole evaporation may portend a scientific revolution as significant as the birth of quantum theory itself. Proposed resolutions exist. Information might be encoded in subtle correlations within the Hawking radiation, or stored holographically on the event horizon itself. The 2020s saw significant progress using tools from quantum information theory, suggesting information may be preserved after all. But a complete, universally accepted resolution, consistent with both general relativity and quantum mechanics simultaneously, does not yet exist. 2. The Fermi paradox. The Milky Way contains an estimated 100 to 400 billion stars. A significant fraction host planets. Some fraction of those planets sit within habitable zones. Earth shows that given billions of years, simple chemistry can become complex biology, and complex biology can become technological intelligence. Run those numbers across a galaxy 13. 6 billion years old, and the conclusion seems unavoidable. The galaxy should be full of intelligent civilizations, some of which should have had millions of years longer than humanity to expand, build, and signal their existence. We see nothing, no signals, no probes, no structures, no evidence whatsoever anywhere of any other technological civilization. This was formalized by physicist Enrico Fermi in an informal 1950 conversation that became known as the Fermi paradox, usually summarized in 3 words. Where is everybody? The paradox persists because every proposed resolution requires assuming something we cannot currently verify. Perhaps complex life is far rarer than the numbers suggest, the rare Earth hypothesis. Perhaps civilizations reliably destroy themselves before becoming detectable, the great filter. Perhaps advanced civilizations deliberately avoid contact, or exist but use communication methods we cannot detect. Or perhaps we are simply too early, the first technological species in a galaxy still too young for others to have emerged. Every explanation is consistent with the absence of evidence. None of them can be confirmed with the evidence we have because the evidence we have is nothing. 3. The grandfather paradox. General relativity permits mathematically the existence of closed time-like curves, paths through spacetime that loop back on themselves, allowing an object to return to its own past. Certain exact solutions to Einstein's field equations, including rotating universe models studied by Kurt Gödel in 1949, contain these loops as a direct mathematical consequence of the theory. If time travel to the past is physically possible, the grandfather paradox follows immediately. A time traveler journeys to the past and kills their own grandfather before he has children. The time traveler is never born. But if the time traveler is never born, they could never have traveled back to commit the killing. The grandfather survives. The time traveler is born, they travel back. The loop never resolves into a single consistent timeline. This is not a philosophical puzzle invented for entertainment. It is the direct logical consequence of solutions that are mathematically permitted by general relativity. Several resolutions have been proposed without full consensus. The Novikov self-consistency principle, proposed by physicist Igor Novikov, suggests that any action taken in the past must already be consistent with the history that led to the time travel in the first place. The universe simply does not allow contradictory actions to occur. Physicist David Deutsch proposed in 1991 a quantum mechanical resolution using closed time-like curves at the quantum level, in which a consistency condition naturally prevents contradictions without restricting the time traveler's choices. In December 2024, physicist Lorenzo Gavesino published research suggesting that thermodynamics itself behaves differently on a closed time-like curve, with entropy potentially reversing in ways that could resolve the paradox. None of these are experimentally confirmed. No closed time-like curve has ever been observed or constructed. The paradox remains a live question precisely because the physics that would resolve it has never been tested. 4. OLBERS paradox, resolved, but worth understanding why it took so long. If the universe is infinite, eternal, and uniformly filled with stars, then in every direction you look, your line of sight should eventually terminate on the surface of a star. The night sky should be uniformly, blindingly bright. Instead, it is dark. This contradiction, named for astronomer Heinrich Olbers who popularized it in 1823, took over a century to resolve correctly, and the eventual resolution required knowledge that did not exist in Olbers' time. The universe is not infinitely old, and it is expanding. Light from sufficiently distant stars has not had time to reach us, and the light that has reached us from extremely distant sources has been redshifted by cosmic expansion into wavelengths the human eye cannot perceive. Olbers' paradox is included here specifically because it demonstrates something important about every other paradox on this list. A genuine contradiction in physics is not a sign of error. It is a sign of missing information. Olbers' paradox could not be solved with 19th century physics because the universe's age and expansion were unknown facts, not logical errors waiting to be spotted. The other paradoxes on this list may be in the same position right now, waiting for information we do not yet have. 5. The cosmological constant problem. This is widely regarded as the worst theoretical prediction in the history of physics, and it remains completely unresolved. Quantum field theory predicts that empty space, the vacuum, should have an energy density arising from the constant appearance and disappearance of virtual particle pairs throughout all of space. This is not speculation. The reality of this vacuum energy is confirmed by the experimentally measured Casimir effect. When physicists calculate the expected magnitude of this vacuum energy using quantum field theory and compare it to the actual value of the cosmological constant measured through the observed accelerating expansion of the universe, the two numbers differ by a factor of approximately 10 to the 120th power. This is not a small discrepancy requiring minor correction. It is the largest mismatch between theoretical prediction and observation in the history of science, a number so large it has no meaningful comparison in everyday experience. Something is canceling out all but an infinitesimally small fraction of the predicted vacuum energy, and no mechanism for this cancellation has been identified. Two of the most successful theories in physics, quantum field theory and general relativity, directly contradict each other on the value of a single number, by 120 orders of magnitude, and physicists do not know why. 6. The EPR paradox. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper intended to demonstrate that quantum mechanics must be incomplete. Their argument centered on entangled particles, pairs of particles whose quantum states are correlated regardless of the distance separating them. According to quantum mechanics, measuring one particle instantaneously determines the state of the other, no matter how far apart they are. Einstein, Podolsky, and Rosen argued this implied either faster-than-light influence, which would violate special relativity, or that quantum mechanics was missing some deeper, more complete description involving hidden variables that determine outcomes in advance. For nearly 30 years, this remained a philosophical disagreement, until physicist John Bell derived a mathematical inequality in 1964 that any theory based on local hidden variables must satisfy. Quantum mechanics predicted this inequality would be violated. Experiments beginning with a Lane aspect in 1982 and refined repeatedly since confirmed that nature does violate Bell's inequality. In 2022, Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics specifically for these experimental confirmations. The experiments resolved which side of the original argument was correct, quantum mechanics, not local hidden variables. But this resolution does not dissolve the paradox. It sharpens it. The universe genuinely exhibits correlations between distant events that cannot be explained by any local classical mechanism and cannot be used to transmit information faster than light, yet are demonstrably experimentally real. Physicists have a mathematical description of this. They do not have a physical explanation of how it works in any sense that resembles ordinary causation. 7. The Horizon Problem. The cosmic microwave background, the oldest observable light in the universe, has nearly identical temperature in every direction we look, varying by only about 1 part in 100,000. This should be impossible under the standard Big Bang model without modification. Regions of the universe on opposite sides of the observable sky are, under standard expansion, separated by distances so vast that light has not had time to travel between them since the Big Bang. They have never been in causal contact. They could never have exchanged the energy needed to reach the same temperature through any known physical process. And yet they are at the same temperature to extraordinary precision. This contradiction, uniform temperature across regions that should never have been able to influence each other, is the horizon problem, first identified clearly by physicist Wolfgang Reindler in 1956. The leading proposed solution is cosmic inflation, proposed by Alan Guth in 1981, an extraordinarily rapid exponential expansion in the first fraction of a second after the Big Bang, which would have allowed regions that were once in causal contact to be stretched far enough apart to explain the current horizon problem. Inflation solves the problem elegantly on paper, but direct observational evidence for the inflationary epoch itself remains indirect and incomplete. The specific mechanism that drove inflation, the inflaton field, has never been directly detected. The horizon problem has a leading theoretical solution that has not yet been confirmed with the same rigor as the paradox it solves. Paradoxes are not flaws in the universe. They are flaws in our current understanding of it, made visible by the collision of two theories that each work extraordinarily well within their own domains, and fail completely when forced to agree with each other. Every resolved paradox in the history of science followed the same pattern. Two things that seemed impossible to reconcile turned out to both be true,